Hey everyone, Mr. Fransky here. We're going to jump into Chapter 4 today, which is talking about applications of derivatives. Let's use a little bit less offensive color. How about that? Let's do purple today. Why not? So, what we're going to be looking at first is extreme values. This is 4.1. Chapter 4 is going to be all about kind of taking the derivatives we've been talking about. Right now we know that that gives you the slope of the tangent line of a function anywhere, but it's like, how do I apply that to anything useful? So today, Chapter 4, we're going to be able to jump in and go a little bit deeper. I made this video once already, and there were a bunch of mistakes in it. So if you're watching this one, this is the correct version. If you want to see a video with a bunch of mistakes in it, it's still on my YouTube channel, so you can go find it if you want to, but it's not on our Schoology page anymore. So today students will be able to find the extreme values of a function and where they occur by using calculus. Let's take a look. So, vocabulary derivative, we've been talking about them a lot. Maximum, minimum, critical points. That's something new we'll be talking about today, where critical points of a function occur. All right, so extreme value theorem. So the extreme value theorem says, let's just write it out and then we'll kind of talk about, we'll unpack a little bit. So extreme value theorem says that if f of x is continuous on closed interval ab, it's important that it's closed. So if f of x is continuous on closed interval ab, I guess I'm going to capitalize, then f of x has a maximum and minimum value on closed AB. Okay, so what that means is if you have a function that is continuous from a closed to another closed, let's say something like this. Yeah. Okay. It doesn't have to be differentiable. This one looks like it would be. It's pretty smooth. But the point is, if you have, so this is A over here, and this is B over here. So on AB, because it's continuous that entire time, there's going to be a maximum and minimum value. So it looks like the minimum value is right here. It'd be f of A. The maximum value looks like it happens right there. So any function you have, even if it's not continuous, or if it's not differentiable, excuse me. So if you have like a cusp, right, or a corner, right? Even, well, no, it has to be continuous, so it has to be something like that. You still have a maximum and minimum value as long as you're starting somewhere and ending somewhere, right? So in this case, it looks like that'd be my maximum, that'd be my minimum. Here it looks like that's the maximum, here's the minimum, okay? But every function that is continuous on a closed interval has a maximum and minimum value somewhere on that closed interval. Okay, so it doesn't seem too bad, and I like because it's called the extreme value theorem. So look how extreme those values are up at the top and the bottom, right? So, differentiability implies continuity. AP uses this a lot. So a lot of the time, they won't tell you that a function is continuous, but they will tell you that it's differentiable. Okay, so they'll tell you a function is differentiable, and you have to imply that that the function is continuous. So they could tell you like f of x. They could say f of x is differentiable on something like closed -3, 5. Okay, this tells you that the function is continuous. Okay, so they're implying the function is continuous also on closed -3, 5. Okay, and then having that information, you can use the extreme value theorem, which says that there's a maximum and a minimum value between -3 and 5 somewhere. Okay. Now, this is important. The converse of this is not true. If it's continuous, that doesn't necessarily mean that it's differentiable, right? We know that when we tested for differentiability, like one of the first things we checked was, is the function continuous? And then we did some other tests to see if it was differentiable. But, so it makes sense that if they tell you it's differentiable, that they already checked to see if it's continuous. But the converse isn't true, right? We have lots of functions that are continuous that are not differentiable, right? If you have a corner or a cusp, so if you have a corner or a cusp, those are functions that are continuous. You can draw them without lifting your pen, but they are not differentiable. So be careful with that. If they tell you it's continuous, that doesn't mean it's differentiable. But if they tell you it's differentiable, that does mean that the function is continuous. Okay? So AP, lots of the time, they'll say f and g are two functions that are differentiable on their entire domains. They'll say something like that, something cute. All right, so let's find the minimum value, maximum minimum value of f of x equals x squared on the interval -1, 2, and they want to know where they occur. So to do this problem, what I'm going to do, I'm going to sketch a quick graph of this. You can't always graph it, but in this case, x squared isn't too bad. So from -1 to 2, our x squared graph is going to look something like this, right? Okay, so it's closed -1 to 2. It looks like we definitely have a continuous function there. Excuse me. So if we take a look at this, it looks like our minimum value happens right here at 0, 0. So it has a minimum value of 0, so if y equals 0, and that happens at x equals 0. So you probably talked a lot about this in pre-calc. Things happen at x values, and the values are y values. We talked about this with motion too, right? So things happen at x values, and the value is a y value. It has a maximum value of, looks like at 2, so I plug 2 into x squared, it gives me 4. So it has a maximum value of 4, and that happens at x equals 2. So 4 is the y value. Okay, so the value maximum is a y. The place that it happens is at an x coordinate. Okay, so not too bad. Now, relative versus absolute max and min. So if I draw something like this, let's say I have a function, let's say it's a cubic. Let's say it looks something like this. Okay, yeah, like that. So here's our a, here's our b. And let's put in some other letters here. Let's say this is, let's actually give these some numbers. Let's say this is -1. Let's say this is -3. Let's say this is 4. Why not? Let's say this value right here is 2. And let's say this is 1. Let's say this is 2. Let's say this is 5. And let's say that this right here is like -2. Okay? So, a relative extrema, So relative extreme point means that if you just look around that point, it's the top or bottom of the world, right? So if I only look at like this much of the function, it looks like that is the end of the world. It's for sure relative minimum, okay? Same with this guy right here. If I only look at this much of the function, it looks like that's the bottom of the world. That's a relative minimum, okay? So relative just means that locally. Sometimes you hear this also called a local maximum or a local minimum. It just means that around the point, so around the point, it's the max or min. It's the max or min. Okay? Absolute means that there is no point higher or lower anywhere on the graph. No point higher or lower. And there are a lot of functions. So if I talk about like an absolute maximum, there can be no point higher. A lot of functions don't have this, right? Like a lot of polynomials, like cubic function, goes up and down forever. There are no absolute extrema. In fact, there are no relative extrema either because it's always increasing. Okay, so for this guy right here, if I think about finding the extreme. So it looks like I have a, let's talk about our minima first. So relative minimum. So I have a relative minimum. The value is, let's see here. So we start with a relative minimum at -2, and that happens at -3. -3. We have a relative minimum of 1 at x equals 2. And the -3 one, this actually happens to be an absolute. Right? So it's a local, it's also an absolute. And then our relative maxima, so we have one that is 5 at -1. And we have a relative max of 2 at x equals 4. And this relative max at 5 at -1 also happens to be an absolute. So these two are kind of special, right? Because they're absolute maximums on the closed interval. And extreme value theorem tells us because we're continuous on the closed interval, there should be a maximum and a minimum. So what about this? Sometimes you'll get functions that look something like this. And this is going to be the simplest example that we can have. Let's give these some values again. Let's say this is -3 and -2. Let's say this is 2 and 1. So if I ask you, does this have a maximum value and a minimum value? And the answer is no. At this hole right here, we can get really close to 1, as close as you want. If you tell me the maximum value is 0.999, I say, well, I can get closer though. What if I say 0.9999? Right? And then you say, okay, that's the maximum. Then I add another 9. Then I add another 9. There's never a value that you can get that is the closest you can be to 1. I can always find a number closer. Right? Same with the minimum. I can get really close to -2, but I can't ever get there because of the open circle. And this is only continuous on open -3 to 2, right? It doesn't include the endpoints. This is why extreme value theorem is still satisfied, because we don't have a closed interval. So this actually has no max and no min. This confuses students a lot. They'll see a picture of something like this with a hole at the top. This doesn't have a maximum value. It gets really close to that y value, but it never gets there, right? So you have to kind of be careful about functions like this that have discontinuities, because the extreme value theorem does not apply. AP loves to ask questions like this. They'll do like, it's continuous but not differentiable. It's differentiable but not continuous. They have all kinds of problems like that we'll see later on in the chapter. All right, critical points. So the definition of critical point. The definition of a critical point is if f prime of x equals 0 or is undefined. Okay, so for example, let's say you have a derivative. So let's say you have some function where f prime of x is equal to x squared minus 1 over x. Okay, so your critical points for this, critical points are going to be things that make it 0 or undefined. So it's 0 at plus and minus 1. So 1 and negative 1 both make this derivative 0, and 0 makes it undefined because it makes the bottom 0. So the interesting things about critical points is that maxes and mins, there's only two places they can happen. They can only happen at critical points and endpoints. I'm going to say or endpoints. And let's look at our last function to see if that's true. So look at this. Look at where our maxes and our mins happen. The max happens here where the horizontal tangent is 0. Here it's also 0. Those are critical points because the derivative is equal to 0. The endpoints are the other place that maxes and mins happen. Any other point that is not one of those is going to just kind of be like one of these boring points, like in the middle of a line, right? But a max or a min has to happen at a critical point. Now, what would it mean if it was undefined? Well, that would be like if I had a corner, right? Is that a maximum? Absolutely, right? It's a local maximum. Nothing around it is any higher. And in the way I just drew it, it's actually an absolute as well. But the derivative there would be undefined, right? The derivative at that point would be undefined because it's a corner, okay? Not too bad. All right, so we're going to be able to use a calculator on this one. We're going to find the maximum and minimum points on this function. And notice it's closed interval, so the extreme value theorem should apply because this function should be continuous between 1/2 and 5/2. So let's see if we can figure this out. The reason I know that it's continuous is because sine of x, so 1/2 radian and 5/2 radians, these is kind of weird numbers, right? If we think about them as decimals, 0.5 and 2.5, think about the unit circle. This is 0 radians, this is pi. Remember pi is 3.14159, blah, 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 right? So these are both positive values. 0.5 radians, you don't have to know exactly where that is, but that's like over here somewhere. 2.5 radians is going to be short of pi. It's going to be like over here somewhere. That entire time, sine is greater than 0. And taking the natural log of a positive number is okay. You can't take the natural log of 0 or a negative number. So I know that I'm continuous. Awesome. You could also graph it to see that, but we just kind of did it analytically. So now what I'm going to do is I'm going to find my critical points. So I'm going to find f prime of x. F prime of x in this case is 1 over sine x, right? Because it's natural log. Derivative of natural log is just 1 over sine. And we multiply by the derivative of the inside function, which is cosine x. So that is cosine x over sine x, which is cotangent x. Okay? All right, so that's our derivative. Now we have to think, is cotangent x undefined or 0 anywhere between 1/2 and 5/2? Well, if we look at our kind of cosine over sine here, cosine is 0 at pi over 2. So x equals pi over 2, if we're thinking about our critical points. So x equals pi over 2 gives us a derivative of 0. And x equals, let's see, if we have anything that's going to make us undefined. I don't think sine x is ever 0, because sine x is 0 at 0 and pi, but those are in our interval. So that's our only critical point, is x equals pi over 2. So then if we're thinking about maxima and minima, the x values we have to test, this is called the test point method. We're going to use the endpoints, 1/2, then pi over 2, and then 5/2. Okay, so let's see if we can figure out these values. So 1/2, I'm now going to plug them into the actual function, f of x. So here we'd have natural log of sine of 1/2. All right, I'm going to plug that into my calculator real quick here. Natural log sine of 1/2. Make sure I'm using radians, and hit enter. Gives me negative 0.735. And then if I try pi over 2, well, I think I can do that one. Sine of pi over 2 is 1. This is a natural log of 1. Natural log of 1 is 0, because e to the 0 is 1. Then 5/2, I have to go back to my calculator. So I'm going to do natural log of sine of 2.5. 2.5. And that gives me negative, so natural log sine 5/2 gives me negative 0.513. Okay. So now what I'm imagining here is the critical point, the whole idea of critical points is that these are the only places the maximum and minimum can happen. So what must happen is all the other points must be boring. So at 1/2, I'm down here at negative 0.735. Then I must increase up to 0 when I get to pi over 2, then back down to negative 0.513, something like this. So it looks like our maximum value is 0. And our minimum value is going to be this negative 0.735. and that happens at x equals 1/2, and this happens at x equals pi over 2. So, not too terrible. Hopefully this wasn't too painful. But try the next videos. I'm going to get to go to the mean value theorem next, which is one of the coolest theorems in calculus. So, love you guys. That's why I'm here. Have a great day.